of all, thanks to Wajing and the other organizers for giving me the opportunity to speak today. And what Wajing asked me to do is give an introduction to the soft collinear effective theory that would be suitable, not just for people, so that the talk would be suitable for people that know about effective field theory, but know nothing about SCT. So here's the outline of my talk. And what I'll start by doing in the first kind of more than half of the time is by just going through some of the basics of how this EFT is constructed and what kind of things it describes. So we'll start about talking about what is the scope. Wajing already mentioned a bunch of things that it can be used for. Then we'll talk about what every effective field theory has to talk about, which is how is the power counting set up? How is it organized? What is its Lagrangian? How do things interact? In soft collinear effective field theory, there's a special role played by Wilson lines. So we'll talk about why that is and where these Wilson lines show up. And there's also something that arises known as factorization theorems or factorization formulas. And that's because of the way that things just interact with each other and talk to each other. So that will also be something that I'll talk about. Now, like any effective field theory, there's sometimes large logarithms and you want to sum them. And this effective field theory is no different than those. So we'll talk about how that works. It's a little different in soft collinear effective theory than in some other examples you may be familiar with, like SNEFT is different than SCT. And then there's something called forward scattering that also plays a role, and I'll mention that. So this is kind of about formalism. And then to have some applications, what I decided to do is just to highlight a few particular applications drawn kind of picked to highlight different aspects of SCT because it's a pretty broad field. And I've also picked them to highlight some work going on by members of my group. So the applications will be to high precision resummation, to the description of power corrections beyond leading order in the EFT, something about the Regge limit, and then something about jets, but not just jets, but inside jets, known as jet substructure. So please, as I go through my talk, if you have a question, feel free to interrupt. And if I don't get through all 4 applications, then that's totally fine. Okay, so as Wajing already said, soft collinear effective field theory is an effective field theory that describes short and long distance physics, like a lot of effective field theories. But in this case, it's in particular for collider physics. So we're interested in QCD, where there's some short distance high energy collision that causes a short distance process to occur. And then it produces energetic particles, which will be collinear particles in my talk, as well as perhaps soft particles. And that's what soft collinear effective theory describes, is the interplay between those hard interactions and the long distance physics, which is either collinear or soft. Now, if you just I could write down processes, but I wouldn't be able to fit them all on the same page, because STT is this is a very broad program. It's effectively the collider physics program. So it just categories are things like Higgs production of other heavy particles, jet physics, the description of the formation of jets, as well as jet substructure, what's inside the jets. SCT has its origins in the description of B decays, heavy meson decays, rare decays, and CP violation. I won't talk about that at all today. There's also Quarkonia phenomena combining SCT with NRQCD. I won't talk about that either. And then there's applications to nuclear physics with transverse momentum distributions, as well as heavy ion collisions. And I won't really have time to, I'll briefly touch on one example in the TMD category. That's kind of on the phenomenological side. So there's lots of different applications that SCT can be applied to. On the field theory side, there's also a number of topics here that I've just highlighted to show you kind of what type of ingredients that I can learn about field theory just from using an effective field theory. And so there's higher order resummation. How do I carry out the resummation of large logs, not just the leading log or next to leading log, but next to next leading log, or even next and next and next to leading log. So that's, I'll give you an example of that. You can learn about the infrared structure of gauge theory, including gauge theory at subleading power. So this is something that the EFT can teach you, and how to organize, for example, subleading power is natural from the EFT point of view. There's a connection to fixed order that I won't have time to talk about today, but so-called subtraction techniques are something that the EFT is helpful for understanding and improving. And then there's a connection to Regge phenomena, and I'll give you an example of that. So the basic process to have in mind is that you have some kind of hard collision. Maybe you have two protons at the LHC. There's a hard collision of partons at short distance. And then you produce a number of things, including maybe some leptons, as well as some jets. And you want to describe the physics of this process, which is a multi-scale process. And that's what SCT is going to allow us to do. So the first thing that we want to do is we want to split the physics into different momentum regions. So I'm just going to go through this, and I'll go through it a little bit slowly just to make sure that, that I don't go too quickly right at the beginning. So what are collinear splittings? So the idea is that you have some hard process. It has produced a very energetic particle. Maybe it was a gluon, and it's traveling along with some large momentum. So let's say it's moving in the z direction. Then its large momentum will be its energy plus its large z momentum. And if it's a massless particle, then its momentum minus its z momentum will be small. So we can imagine that it has a large minus momentum along its direction of motion in this direction. Then this particle could split. It's a massless particle. It could split into a pair of gluons, for example. The pair of gluons will now have some transverse momentum. And the idea is that we're imagining that we're working in a limit where the transverse momentum is much smaller than this large minus momentum, which is the sum of the energy and the z momentum. So this is our power counting parameter. So and that's expanding in a collinear limit because the radiation is collimated in the direction of motion of the original particle. And so we call these particles NCollinear if they're collimated in the n direction. And often to make things simple, we define a light-like vector n. So in this case, n would be 1 comma z hat, and it just is a light-like version of the z hat axis where we just add in a time component. And then we can say that this p plus momentum is the dot product of n and p. And we can also define a complementary light cone vector n bar, which is 1 minus z hat. And then this large minus momentum is just the n bar dot p. So the scaling of the degrees of freedom here, which are called NCollinear, can be just characterized by how the momenta scale. And it turns out that we have the minus much bigger than the perp, as I said. And then on shell, the plus momentum is equal to the perp momentum squared divided by the minus momentum. So it's, again, much smaller than the perp momentum. It's of order p perp squared, which is lambda squared. So we have, in the end, plus, minus, and perp, which have this hierarchy of lambda squared, 1, and lambda. And sometimes we just refer to that lambda squared 1 lambda as the scaling of an NCollinear particle. So that's the dynamics of collinear particles that are collimated in a jet that's produced by some hard collision. And that's one of the types of degrees of freedom that we're going to have to talk about. Another type of degree of freedom is soft emission, because you could have your energetic particle, let's keep it as a gluon, traveling along, and it could talk to some soft radiation. So maybe there's a soft emission, and that soft emission, maybe it has some momentum k that's much smaller. Let's say it's of order lambda squared than the original collinear momentum p that's traveling in this direction. This final state particle here will have momentum p plus k. And it turns out that one important thing that happens when soft particles interact with very energetic collinear particles is something called the multipole expansion. The reason that happens is because the momenta have different scaling. We have a momentum here that has a order lambda squared, much, much smaller than everything but the plus momentum over here. Only the plus momentum was of that size. So when you think about this p plus k momentum, you get the combination n dot p plus k showing up, but you never get k showing up when you have a p perp or when you have a p minus. There's just no k mu's there, and those k mu's are expanded away. So you only have the particles talking through one momentum component. In position space, that's like expanding some of the positions about 0. In momentum space, it's saying that only these two components can talk, and that's effectively what's called a multipole expansion, and it's going to affect the dynamics of how these particles talk to each other. So this is how soft particles come into the game, but there's no suppression from having this process happen of a collinear particle emitting a soft particle or a collinear particle splitting. So these are things that are going to be in the leading power Lagrangian. Now, I said that the SET was the physics of hard scattering, so we should ask about how the hard scattering comes in. And so you can imagine a process where, for example, you have a QQ bar pair, and then maybe you produce a particle. But let's imagine that the QQ bar pair came in two different light cone directions, and say the N and N bar, so they're back to back, and it's a hard collision. Maybe these are two partons from the proton. Then the thing that you're going to produce in that process is what's called a hard particle. So this thing here, because those two particles pump in a lot of energy in two different light cone directions, this momentum here is going to be something that's hard, and it's going to have scaling that's going like lambda to 0, no suppression. And those hard particles get integrated out in the EFT. So you basically integrate them out into some short distance interaction, and then you have your long distance collinear lines, which these outgoing lines could also be two different collinear lines, which might look like that. So you have these particles which are in different collinear directions. We have the incoming ones, which are in N and N bar, and the outgoing ones, which are in N1 and N2. So 4 different collinear directions, all tied together by the hard interaction, which is this gluon that got integrated out. That gives you one example of what type of thing I was talking about with the hard physics. So the EFT would be the effective field theory of these type of operators. Finally, there's another type of effect that can happen, which doesn't have to do with hard scattering, but rather forward scattering. And so this is another way that energetic particles can interact with each other. So let's imagine I have 2 energetic particles in 2 different light cone directions coming along, but they don't hard scatter. Instead, they just scatter by a small amount through a gluon. So there's a T-channel gluon like this. And so there are large momentum components, which would be the minus momentum here, to the quarter lambda 0. And in this other opposite light cone direction, it would be the plus momentum. Those components are conserved. They basically go through the process without changing. And the gluon exchange is not, which is exchanging some momentum, Q here, it's only changing the perpendicular components of, so basically we have a situation where we have forward scattering. So these particles don't hard scatter. If they hard scattered, we would change the collinear direction. But instead, we just scatter to the same collinear direction, and we just change the perpendicular momentum, so it's a forward scattering. And so we have forward scattering with a small transverse momentum deflection. And so this process happens through something that's called a Glauber gluon. So this red gluon here is called a Glauber gluon, and it has the property that its plus momentum times its minus momentum are much smaller than its perpendicular momentum. So it's kind of dominated by transverse momentum, and it acts like a transverse potential in this scattering. Okay, so that's another type of phenomena that we're going to have to incorporate in the effective field theory, because it's another way that 2 collinear particles can interact with each other, not through a hard scattering, but through a forward scattering. You could imagine some outgoing particles in 2 different collinear directions, and then they have a rescattering through one of these Glauber type exchanges. Okay, so that gives you the idea of the players. And so what we're going to do is construct an EFT of that. And so we have what we're going to do is we're going to write down fields for the different things that I was describing, and in particular the on-shell degrees of freedom, which are the soft and collinear degrees of freedom. And so for each of the collinear directions, say if I have this PP collision producing these 3 jets, then I would have quark fields, C, and gluon fields, A, for each collinear direction. So I have them for these green guys, for these other green guys, and then for each of the jets, I have a different set of fields. And the EFT is going to be about how these fields talk to each other, as well as how they talk to their partner in the same collinear direction. And then in addition, there's going to be some soft fields, which is my little orange lines in this figure. And we're going to have to think about the field theory for those fields. Now, if I that doesn't sort of cover all the things that I mentioned to you. In particular, I didn't mention fields for the sort of Glauber or hard interactions. And I only mentioned fields for the collinear and soft. Soft actually come in two different types. That's not going to really be important for my talk, but just sort of for completeness, it depends on whether the momentum are order lambda or lambda squared. But I didn't mention fields for, so there's fields for all these things. They have particular momentum scalings that we already talked about, but there's no fields in the EFT for these Glauber and hard modes. And the reason is that these processes here and these momenta scaling here are off-shell. They're not on-shell processes, they're off-shell processes. So p squared is never close to 0. And so the way that those are treated in the EFT is that we integrate them out. That's kind of the obvious thing to do when you're thinking about the hard modes, because they're at the highest scale in the problem and they're shrinking to a short distance interaction. And it's also, though, how we're going to treat the Glauber interactions. They're going to be treated as a non-local off-shell kind of potential in the EFT, and I'll eventually get to that. Okay, so we have to figure out how these different objects interact with each other. So I should just say that, you know, when I was, this is generalizing what I told you at the beginning, that now there's different n components for each of these n directions. So for each of these different jets, I have a different n, and I have an n hat corresponding to the jet axis, if you like. And I have a decomposition of momenta along these different directions. So you should remember, like when I'm writing these formulas, that it's really talking about different coordinate systems each time. That can be kind of confusing, but once you get used to doing it, it's not so bad. Okay, so let me go through the step by step. So you should think about what's happening in this very short distance blob in the middle as some kind of short distance process. Maybe it's gluon fusion, producing a Higgs particle, or producing a Higgs particle together with some jets, or it could be some standard model process, like it could be gluon-gluon scattering through a quark. Maybe there's an extra gluon emitted. So these could be our incoming gluons from the proton, and then these could be our three jets. And if that was the case, then these intermediate lines would be hard. So this and this, and those would be integrated out, and then that would form our short distance blob. And we would have just a standard model QCD process that has this type of final state. So of course, the problem is disentangling these things. That's part of the collider physics problem, but we also want to calculate cross sections for the different processes, both backgrounds as well as signal. Okay, so this EFT works like every EFT. We sort of integrate out scales one at a time. So let me talk about how that's done. So the first thing to think about is the hard scale. It's the largest scale in the problem. And we want to sort of take QCD. This is a top-down EFT. So we can take QCD and just systematically match onto the SET. And so the first thing to do is just integrate out those hard particles in the way I've described. And that sort of shrinks whatever was happening at the short distance collision that's tying together the collinear particles into a short distance blob. And effectively in the EFT, that means that there's going to be some Wilson coefficients that describe those short distance processes, both the standard model processes, or as well as perhaps some new physics processes, and both electroweak Higgs and QCD all go sort of into these, if it's short distance, it goes into these Wilson coefficients. Eventually, these Wilson coefficients get squared in some cross-section that defines what are called hard functions. And so that language will show up in my talk from time to time. Okay, so I want to give you an idea of kind of what happens in this process of building these operators. And there's a few things to describe in order to do that. So one of them is so there's going to be a few steps here to figure out what these operators actually look like. So one thing to figure out is just what happens when I have a high energy collision. And if I have a high energy collision where I know that the minus momenta are much bigger than the plus momenta, then it turns out that spinors kind of get expanded. So in a high energy collision, there's what are known as good components of the spinor. This is a very old language, goes back to sort of people's study of DIS and DIS at subleading twist. And it was understood that there were sort of good components and bad components to the fermion. And the hard interactions, which set this minus momentum being much bigger than the plus momentum, they define a frame for talking about the interaction between different collinear particles. Those hard interactions couple to the good components. And that means there's a projection relation on the fermion fields in the hard operators. And it makes sense to talk about those fields of the good components as sort of the field you want to describe in SCT, because it's the one that the hard interactions are coupling to. So if we talk about those good components, then we can also think about the power counting for those good components. And this works the same way it works in any effective field theory. What you do is you look at the kinetic term, and the kinetic term is sort of how you normalize things to get going, and that's going to determine the power counting. This is not sometimes that's very simple. You just think about the kinetic term, it sets the mass dimension for your field, and you have a mass dimension power counting. This is not that way. And it's partly not that way because there's an obvious breaking of Lorentz symmetry by the presence of the hard interaction and picking out these particular directions. So the power counting is going to be a little more complicated here, but it follows the same paradigm. You just look at the kinetic term and that tells you how to figure out the power counting. So remember that the power counting expansion parameter was this lambda. It was the thing that was small. And so here's how the power counting works for the collinear fields. You write down the collinear propagator formula. That's a time-ordered product of two collinear fields integrated over space-time. And if you look at the leading propagator for these good components, it looks like this. You just sort of expanded the p slash in the numerator. And you have a p squared in the denominator. Well, the p squared in the denominator has both plus momentum times minus momentum as well as per momentum squared. But that all scales like lambda squared. The numerator scales like lambda to the 0. So this propagator scales like lambda to the -2. The measure in this calculation scales inversely to the momenta, and the product of the momentum is lambda 4, so this measure scales like lambda to the -4. And then just balancing the equation tells you that this product of fields has to scale like lambda squared, and therefore the fermion field scales like lambda. So each addition of a lambda here is actually kind of like counting twist. Each addition of a lambda is like going up 1 power in twist, but each field here has a power counting of lambda. And you could go through the same type of exercise for other fields in the problem. It turns out that the gluon fields scale the same way as the gluon momenta. So that's got an interesting scaling for this collinear case, a less interesting scaling for the soft or ultra soft cases. And then that just determines the power counting of your fields. And then you can start building operators out of them. So your power counting of your fields determines the power counting of products of fields, which are operators. And then from that, you can build Feynman diagrams and figure out the power counting for the Feynman diagram. And just like other EFTs, like Kyle perturbation theory or various EFTs that don't have like just simple dimension counting, you can derive a power counting theorem that tells you the scaling of any Feynman diagram in the field theory or any time-ordered field theory, just on what are the powers in the Lagrangian. Or just, if you like, just based on the vertices in the Feynman diagram, not based on propagators or loops. You can remove those things with Euler identities. And the same type of paradigm happens here. I won't go through the details of describing how that works, but there's a power counting theorem that tells you how to construct leading power operators. And so what kind of thing do you get out of that? Well, you get a Lagrangian that organizes itself in the following way. So it can be split into sort of 3 parts, and I'll talk about these 3 parts one by one. So there's a part that's related to the dynamics of how soft and collinear fields interact with each other. There's a part related to connecting collinear fields together, which is this hard interactions that I was already talking about. And then there's those globber interactions, which are kind of special for reasons that I'll talk about. So the hard interactions are what I was already saying. So at leading power, at lowest order in the expansion, you might have some set of Wilson coefficients and some set of operators. And then if you go to higher orders, you have some higher order Lagrangians that are describing higher order hard interactions. And so you have to identify sort of the leading operators for your given process, and then you sort of know where to start with your hard interactions. And oftentimes they're only going to appear in your process once because you know there's one hard interaction, and then you have dynamics on top of that. And more than one would be power suppressed. Then the dynamic part of the Lagrangian actually splits itself into 2 different components, or actually multiple different components. It turns out that for a good, almost to a good extent, it splits itself into sort of dynamics of collinear particles interacting with other collinear particles of the same type. So sum over n of Lagrangians n, and then soft particles interacting with other soft particles. There's a little subtlety here related to what's called soft collinear factorization that I'll come to. But it basically, after that's done, then it has that property that it splits itself, where these things don't interact with each other. They only interact with their partners of the same type. And that leads to this idea of factorization, that the dynamic part of the Lagrangian is just kind of a copy of QCD for each type of particle. The hard interactions cause the particles to talk to each other. And as long as this Glauber Lagrangian is not doing anything, so it sort of can cross it out, then we have a factorization of the process where sort of we just have a factorization at the hard scale and then independent dynamics of the particles going out. So I'll come back and say more about that in a little bit. So collinear Wilson lines are something that show up in the problem, and that's related to integrating out hard physics. When you integrate out hard physics, it turns out that you produce interactions of those gluons which had order lambda 0 power counting. And the dynamics of those gluons are actually determined by what are called Wilson lines. So you just go through the process of integrating out hard particles, and that produces some stuff like this that is actually the Feynman rule for a Wilson line. So in position space, this would be a path-ordered exponential of these order lambda to the 0 gluons. And those Wilson lines just come along with your quark fields. Whenever you try to interact with some other type of object in a different collinear sector, you're going to have things that are off shell in the way that I drew in this figure. And that produces this Wilson line when you go through the process of integrating out the hard particles. And so it's kind of like every collinear field, every collinear quark or collinear gluon comes along with an attached Wilson line. And so instead of talking about these things individually, we often lump them together into what's called chi, which is just this quark field times the Wilson line. And that's kind of the more fundamental object in SET. It's actually also in QCD the closest thing to what you would call a parton, but it's kind of taking the charge of the quark and dressing it out to infinity at long distances, and then you can sort of think about things at very long distances without the short distance QCD dynamics in there. But this object kind of naturally appears in the EFT, and it's like a fundamental building block of operators in the EFT, because this process of being dressed by these collinear Wilson lines is sort of important for the gauge symmetry structure of the theory. So these are the fundamental objects that the operators get built out of. So if we go back to our process here, where we had a hard scattering with different collinear directions, you might imagine that the incoming particles are gluons, and maybe 2 of the outgoing jets are quarks, and one of them's a gluon. I guess this one was the gluon in my numbering. And then you have a building block object also for the gluons. It's basically a gluon field strength dressed by an adjoint Wilson line in the same way that this was a quark field dressed by a fundamental Wilson line. And we build operators out of products of these building blocks, and that's it. So it turns out that these building blocks, the gluon building block and the quark building block, suffice to build all operators as long as I sort of add one more thing at subleading power. I also sort of get powers of the transverse momentum. But together, those building blocks suffice to build hard scattering operators in the EFT. And then we also have some ultra soft or soft fields, which I'm not describing. But as far as the collinear dynamics is concerned, those are the only things that we need to build operators. So this might be the leading power operator for this process of hard collision producing 3 jets. Now the jet dynamics itself, of course, there's all this splitting and there's the coupling of to the ultra soft fields, and I have to talk about what's going on, because this is still sort of in the dynamics. There's still a coupling there, and it turns out that I can do what's called a soft collinear factorization or soft collinear decoupling because of the way that the multipole expansion works in the EFT. That multipole expansion basically leads to iconal interactions of the soft particles with the collinear particles. And those iconal interactions can be factorized into another set of Wilson lines called soft Wilson lines. Here, the way that it works in the EFT is that you can write down a Lagrangian where they couple, but they only couple in a special way with one type of covariant derivative. And then you can decouple them by making a field redefinition, basically by redefining the collinear field with a Wilson line that's a soft Wilson line. And then likewise for the gluon fields, which is kind of an adjoint version of the field redefinition. And then due to the properties of the Wilson lines, you go from a Lagrangian where the fields are interacting to one where they don't. So this is this thing the subtlety about that I mentioned. But once we make that field redefinition, we've decoupled the soft and the clear fields. And basically what that does is put all the interactions of the soft fields at leading power into these Wilson line objects. And that simplifies things because they move out of the dynamic Lagrangian and they show up into the hard scattering operators. So if I go back to my scale picture, I can now talk about decoupling these little orange soft lines by thinking about what happens at this scale of the collinear dynamics. And if I do that, the collinear dynamics just turns into lines, which are Wilson lines. And the objects that are defined by the dynamics that's all been shrunk into these lines are what are called jet functions for the final state jets or beam functions. So they're describing all the collinear splittings of these objects. And I'm sort of building up a cross-section formula that's got sort of those hard interactions and then some of this collinear dynamics and then some dynamics at longer distance as well. So what is the dynamics of the soft? Well, the soft are described by just these Wilson lines. And I have different type of Wilson lines. What do the Wilson line know about? It knows about the direction because it's a line along some direction. And it knows about the color representation, whether it's a quark or a gluon, fundamental or adjoint. So some of these S's are curly, that's supposed to be for the adjoint. Some of these S's are Roman, that's supposed to be for the fundamental. And then the soft dynamics is just like a matrix element integrated over phase space, and that gives what's known as a soft function. So the soft dynamics that sort of happens at this soft scale gives some kind of function that's just described by those Wilson lines. And now we're sort of seeing, if we add in addition the factorization that happens from the part-time distributions, which is the kind of final ingredient and involves splitting these beam functions into sort of perturbative and non-perturbative parts, then we sort of have a full factorization of the process into these different ingredients. And it's really this factorization of Lagrangian where it says the dynamics is independent of how these things evolve that allows these things to be split in this fashion. So that's this factorization property that I mentioned. So kind of to summarize, sort of a factorization of Lagrangian into independent dynamical pieces, factorization of hard scattering operators into sort of hard, collinear, and then once we make the field redefinition, some soft pieces. And it's important that the measurements that you make aren't too wild, so they should also sort of factorize into talking about the contributions to those measurements from different sectors. And then altogether, you get what are called factorization theorems in the EFT. And so there's different ways of thinking about those factorization theorems, but a kind of useful way of thinking about it is to separate things into the lowest scale, which is this non-perturbative scale, and then the higher scales, because the higher scales are going to be some perturbative scales that you can treat in perturbation theory. And so that's what I've done here. I've sort of split the cross section into these PDFs, which are non-perturbative, and then some shorter distance physics, which is perturbative. Now, there could be some long distance physics also associated to hadronization. So sometimes it's not just initial state, but also final state. So I allow for that as well. And then the shorter distance physics, which is the perturbative physics, also involved multiple scales. And it was useful to have this kind of factorization of that short distance physics into different pieces, because the treatment of those scales individually means that we can sum large logarithms that are going to show up in this problem. And that actually show up. They're very important to sum because they show up actually as double logarithms in these processes. So there's a couple of simple examples of factorization. So one that's pretty familiar is just PP to Higgs plus anything. Summing over the final state, summing over everything in the final state means that basically we don't have any of those jet functions. And we have a very simple initial state, which is just part-time distribution functions. And then these things talk to each other through their order one large momenta, which is shared sort of by the collinear functions and the hard function. And that's why you end up with these integrals. So you can think of it as kind of a mixing if you think about each operator as being labeled by a hard momentum. And then there's an integral that ties together the Wilson coefficients, giving these hard functions, and the collinear operators through the kind of momentum components that are of the same size power counting. And that tells you sort of how the convolution structure of these factorization theorems work out. So that's a detail that I didn't get into earlier. But that deriving a formula like this using SET, once you realize what the ingredients are, is actually quite simple. You can kind of do it in a page. So you have here Parton distribution functions. You don't have any of these Glauber effects or soft effects. It's just a hard collinear type factorization. Another process that you might be interested in is producing jets in E plus E minus. Historically, this was used, for example, to measure the strong coupling. This is a simpler process, but then you can ask questions about some observable that's introducing a long distance scale, like, for example, thrust, or the sum of the jet masses of a dijet. And when you do that, thrust is actually very closely connected to that sum of the jet masses. When you do that, you introduce more scales in the problem, and it turns out that the soft physics doesn't cancel out in this case, because you can have soft particles contributing to those jet masses or thrust, and you get a factorization theorem that ties together sort of the hard dynamics, the jet dynamics from the dijets in this picture, and then the soft physics that I was talking about. So it's another example of factorization, this time where the soft dynamics didn't cancel out. Okay, so I mentioned several times the summation of logarithms. So let me say a few words about that, because I kind of said it's special here. It turns out that when you do the UV renormalization in SET, there's one over epsilon squared poles at one loop, but they show up for a special reason. They show up due to the cusp nature of like interactions. And there's something called a cusp anomalous dimension that appears. In SET, that becomes a UV thing that you can handle with a UV counter term. And a single logarithm shows up in your anomalous dimensions. So usually your anomalous dimensions will not have a log like that, but in SET they can. And the presence of that log leads to Sudakov double logarithms. The fact that these types of equations are homogeneous equations, so I have an RG equation for a hard function that gives back the same hard function, leads to exponentiation. And if I integrate a single log once with respect to mu, I get a double log, and that's sort of an exponential of double logarithms, which is the Sudakov double logarithms or the Sudakov form factor. And then when you go through the evolution in the EFT, it's allowing you to sum logs of some observable that a priori in the full theory didn't even know about scales. But those scales, by splitting it into scales in the EFT, you sort of split it into hard dynamics, collinear dynamics, and soft dynamics. And then you do RG evolution for each one of those, and you can sum up all these logarithms, even if they're double logarithms, like a log squared of tau. So you have a sort of evolution factor that comes from solving the differential equation, as well as some kind of boundary condition. You think of specifying boundary conditions at these lines at the different scales, and then you evolve everybody to a common scale and tie them together. And that's how the factorization sums logarithms. And then you can vary these scales, these fixed order scales. The dependence on those fixed order scales will cancel out order by order in perturbation theory. So as you go to higher order, you should get less and less sensitive to those scales, and that's a way of assessing uncertainties in the summation of logarithms. So when I draw bands from doing some calculation, it's because I'm varying scales like those ones. All right, so I kind of said these things. The exponentiation is in the exponent, and if you go to higher orders, you're basically in the exponent, adding powers of alpha s. And people have gone up to next to next to next leading log order, so quite high order. So large towers of logarithms can be summed, and as I mentioned, it's important to sum them because they show up as double logarithms. When you expand out, for example, the exponential, you're going to get a series of double logarithms in the cross section. The kind of ingredients that you need to do that are high order ingredients, but there's a whole community of people that work on resummation and work on the ingredients, doing the calculations necessary to do these types of resummation. So for example, this cusp anomalous dimension is now known at 4 loops, and many of the non-cusp anomalous dimensions are known at 3 loops. So you really can get to the very last entry of this table. Now, I didn't say anything yet about the Glauber Lagrangian, so I want to come back to that before getting to the applications. So the Glauber Lagrangian actually has the following structure. It can be described as an interaction like a potential between soft and collinear particles, and it comes in two parts. It comes in a what I call two rapidity sector part, which is sort of collinear and soft interacting through a potential, and then a 3 rapidity sector part, which has 2 collinear directions as well as a soft part. And these forward scattering type diagrams, which could be between a quark or a gluon, they're described by actually both parts. So if it's forward scattering for soft and collinear, then it's this part. If it's forward scattering for two collinears, well, it turns out that the soft operator starts out with just a p perp squared, so it sort of just cancels this, and then I just have a potential between the two collinear particles. And that describes these forward scattering processes that I mentioned earlier to you. But there's something else that could happen because the soft operators can have soft emissions. And so if there's a soft emission, then you get sort of something non-trivial from this operator, which is actually called a Lipitov vertex. And so you have three rapidity sectors sort of interacting with each other at the same time. So that's what the Glauber Lagrangian is. Sort of for completeness, I wrote down what all the operators are, but I don't want to spend time looking at that. They're all just constructed out of the building blocks that I mentioned, but it's not too important for my talk, so I will skip over that. So what does Lagrangian actually do? So the reason that this Lagrangian is kind of important is that it actually can violate those factorization theorems that I was telling you about. Because what it does is at leading power, it causes particles of different types to interact with each other in a non-trivial way through this kind of potential. And that violates the factorization of thinking about having an independent matrix element for the soft part of the problem, which are the soft functions, or for the collinear part of the problem, which are, for example, these jet functions. If those talk to each other, I can't describe them by independent matrix elements. I have to describe them together as a single matrix element, and the dynamics is much more complicated. So in that sense, this Glauber Lagrangian spoils factorization by coupling the nodes back together. And it turns out that it's actually the only thing that can do that in a non-trivial way. So the whole problem of proving factorization in an SET language is showing that this Glauber Lagrangian can be ignored. And if you can do that, then you prove factorization. Now it's hard to do that, it turns out, and it's only been done in a few cases. But the basic idea of why it cancels out is due to unitarity. You're inclusive enough on the final state particles that you can sum over those final state particles, and then there's a cancellation of these Glauber effects. Or you can think of it in some exclusive process as these Glauber interactions are producing a phase, and when you square the amplitude, the phase goes away. So that's kind of giving you at least some rough picture for why these effects might not be so important. But the details would be a talk in itself. Another kind of interesting point about that in the context of the hard scattering that we've been talking about is that there are some collider physics processes that are sensitive to factorization violation, i.e., you can write down a factorization theorem sort of ignoring that there could be something violating it, just kind of following your nose without thinking too hard about factorization. And you would lead to something that disagrees with data. So you know that factorization is violated. And this description that I've been telling you says that you should actually be able to think about how it's violated and is there some universality to it or some properties of it for those types of observables by just studying this Lagrangian. This is kind of a field that's in its infancy. We don't have field theory descriptions of factorization violation yet, but in principle, this Lagrangian should allow you to do that. But we'll be talking mostly about factoring problems here in my talk. In the context of forward scattering, I should mention that this Glauber Lagrangian is the leading order description. So you sort of know that it's really something that's there because it really describes how particles forward scatter with each other at leading power. And if you're interested in that, this SCT provides some new tools for thinking about it. Okay, so I have about 15 minutes left. I probably can do 3 applications, and I'll just probably go in order. So let's start by talking about the Higgs QT spectrum. So this is kind of an interesting thing to study. You can think about proton-protons colliding through gluon fusion, producing a Higgs particle at some transverse momentum, and there's some recoil maybe by a jet. And then the spectrum of those Higgs events actually piles up at small transverse momentum. So here's the transverse momentum. Most of the events are in this small region. And it's exactly in that small region where you have to sum logs of QT over MH, the Higgs mass, and those are double logarithms as suitable for a Sudakov type problem. There's also fixed order corrections that you want to include to get high precision. So you have a problem where you sort of need to combine together both a resummation as well as fixed order ingredients. And kind of the way it works is through a factorization theorem. So you can write down a factorization theorem for the leading small qt contributions, and then you can say everything else is a non-singular part that you add on. It turns out that there's kind of a factorization of these different ingredients, which is like the hard and the collinear and the soft, as well as part-time distribution functions. And it happens both, there's logs that show up both in sort of the invariant mass scale, the usual mu that we talk about in dimensional regularization, as well as in a rapidity scale, because there's sort of particles that have the same mu that need to be factored from each other. And it turns out that there's logarithms of kind of both types. Once you do this factorization in rapidity, there's logarithms of a kind of a new type that you also need to account for in order to sum all the logs in this problem. So there's sort of two-dimensional renormalization group going on in this problem, but you could solve it. And that allows you to sum the logs in the way that I was talking about. And people have gone to next and next and next to leading log order. In fact, some work that I did with Wajing was going to this order based on some calculation of a 3-loop anomalous dimension that he did. But let me today talk about some more recent result done by one of my postdocs, Johannes Michel, as well as some DAISY collaborators, and one of my former postdocs, Marcus Ebert. And that is doing Higgs PT spectrum and total cross section with fiducial cuts. So fiducial cuts mean the experimental cuts that, for example, here, Atlas cuts that they're imposing, where you have to have transverse momentum of the, for example, if you're doing Higgs to 2 photons, you have transverse momentum of those photons that are above a certain cut, as well as perhaps some rapidity cuts, which they have. So that produces some kind of acceptance. You're not integrating over all of phase space. You're not producing a total cross section, which has a simple factorization, but rather there's some factor that depends on these cuts that you have to integrate your cross section with respect to. That actually makes the dependence on resummation more important in a way that I'll describe in a second. So why would you be interested in these fiducial cross sections? Well, they're what the experimentalists can measure without extrapolating, so that's a reason to be interested. They're also, of course, constraining coefficients in the SMEFT effective Hamiltonian, like the Higgs squared GG operator. So that can be constrained by these fiducial cross-section measurements. Now, it turns out that these cuts actually make you more sensitive to resummation, because what's happening is you're demanding that the PT of your photon be above some value. So it's no longer inclusive. And that actually, in this plot here, I'm kind of showing you why you get sensitive to resummation. You can think of 0.5 in this plot is the maximum value that the photon PT would have if there was no transverse momentum in the Higgs. The Higgs was 0 transverse momentum, then all the transverse momentum comes in the decay from the mass, and half the Higgs mass is the max. So there's a kind of a Jacobian peak here. And if you go to higher, if you have some recoil, if you have some transverse momentum in the Higgs, it can actually, then the photon PT can be larger than the Higgs mass over 2. And in fixed order perturbation theory, things kind of get a little wild around that Jacobian peak. So you need to do some resummation. There's some large logs in that peak. And if you do the resummation, then things stabilize very nicely. And so this is showing you that by inducing these fiducial cuts, you actually get sensitive, even in a kind of total cross section. You want to think of it as a total cross section. You get sensitive to resummation effects because you're putting cuts on the problem and you're getting sort of logs that are related to how far from this threshold you are. So based on that, these authors that I mentioned, and based on lots of perturbative ingredients, which I won't go through for lack of time, produced results for fiducial cross sections, including resummation and next to next to next leading log order, as well as the 3-loop calculations that are in the literature, and then produced results for both the spectrum, as well as integrating that spectrum with the acceptance cuts. So this is the QT spectrum with the acceptance cuts, and then this is the total cross section with the acceptance cuts integrated over QT. And you see that if you, in fixed order perturbation theory, you have pretty large uncertainties. The fiducial cuts actually give much larger uncertainties than in the fixed order calculation than you would have without them, where things are actually much nicer and seem to be converging. Whereas with once you turn on the resummation, you get actually quite convergent results and much smaller uncertainties. And okay, actually, it's sort of the trend. The new results here are these red ones, and they're trending towards the the Atlas measurements. So both improve precision, smaller, and improve convergence by treating this problem properly. So this just gives you an idea. These bands are coming from varying the scales mu. This just gives you an idea of kind of a high precision application of SET. I'll give you a couple more examples. So another example is subleading power SET, going to subleading orders in the expansion. So not just including the leading logarithms, but also logs that are suppressed by a further power of the observable tau. And this just means going to higher powers in the EFT Lagrangian. So you go beyond the 0th order to higher orders. And you can have various things happen there. You could have an additional particle in your hard operator that's in the same collinear direction. Or you could have emissions that are subleading, for example, and have a subleading soft emission. And when you do that, you get sensitive to new things because, for example, the exact momentum fraction that these two particles carry can be another dynamical variable that your factorization can depend on. So whether the gluon has C and the quark has 1 minus C, and that's another variable that factorization can now depend on. And there's lots of reasons to study subleading power. It's kind of interesting for lots of formal as well as phenomenological reasons, but I skipped through that. And I will mention that you did hear a talk about some of the subtleties by Matthias back in October, and I'm not going to talk about that material today. What I will talk about is one application, which is what's known as semi-inclusive DIS. And that's an application where these next to leading power effects are really crucial because they show up in observables as the first term, and you can isolate them. So what is the semi-inclusive DIS process? So it's basically DIS, but producing an extra pion, so through a fragmentation in the final state. And then you can measure, there's lots of things that opens up to be measured. Well, you measure the transverse momentum of those hadrons relative to, say, some jet axis, and or some axis defined by the initial particles. And then you're going to say that that's a small transverse momentum. So again, it's like the small QT limit of Higgs in that sense. But there's lots of other variables that you can measure in the problem. In particular, there's angles. So you could define an angle with the leptonic plane, and then you can define an angle with the hadronic vectors, and then talk about the angle between them. And that allows you, when you make measurements of the full differential spectrum, to isolate out kind of different components. And it turns out that the different structure functions that show up have different power counting. There's sort of leading ones, which are these blue ones here that show up at leading power. And then there's ones that go like the cos phi or sine phi, which would vanish if you integrated over phi. Phi is the transverse angle of this vector. But you can measure those spectra, and they start at subleading power. So it's interesting for that reason to just sort of think about the factorization of these subleading power W's that are showing up. And then with one of my students, Andrew Gao, as well as the former postdoc Marcus Ebert, we've been working on that problem. And basically the way it works in SET is that you sort of start going through and thinking about subleading power operators, and you have two types, ones with an extra p perp or ones with an extra b perp, in addition to your chi field, going beyond the sort of chi bar chi of the leading power operator. And I'm a bit short on time, so kind of jump to the punchline. That you get, basically what you get from doing this factorization is you get products of PDFs and fragmentation functions, leading and subleading power, one of them leading, one of them subleading, or vice versa. And factorization formulas like this. Now, this had been studied previously by people in the parton model, but there had been no QCD description. Nobody had tried to derive factorization before we started working on it. And there was lots of open questions that people were confused about. So one thing that we proved in this work that we're doing is that you get the same soft function as at leading power, and you can actually absorb that soft function in a particular way that's suitable in TMD physics, the same as what people do at leading power. So that was something that was previously conjectured, but we were able to prove. We were able to prove how the hard dynamics comes into this problem. People had no idea, and how there is actually a new variable that showed up in our analysis relative to what people had done in the literature, because they hadn't properly taken into account this momentum fraction splitting between the quark and the gluon that I mentioned. So this really opens up the door for thinking about this type of physics for these, which is something that's important for the TMD program at low energy colliders as well as at a future EIC, to treating it systematically and going beyond just a tree level description of this physics. We can go to higher orders, try to do resummation, and try to include perturbative corrections. Now, I think I'm going to, for lack of time, I will skip over the Glauber application to some work that I've been doing with one of my students, Regge, and I will go to the final example just because I think it'll be a little quicker. So the final example is kind of in the same thread, but now thinking about jet substructure. So when you do jet physics, oftentimes you can look inside the jet and learn something. And one thing you can try to do is you could try to get rid of some particles that are contaminating that jet. Maybe you have some soft degrees of soft dynamics that's coming in from other parts of the event, and it's not really telling you about the fundamental hard particle that was producing the jet, but it's really contaminating it. And you can do what's called jet grooming to get rid of that contamination. And so one way of doing the jet grooming, which is quite popular, is some technique called soft drop. And basically it just sort of looks at the tree, a branching tree of the particles organized by angles in a CA algorithm. And then it goes through the branching tree, which you can apply to a real event. And it removes particles that are soft. If they don't pass a criteria, they're too soft, then you sort of just cut them out. And that ends up removing with some parameters that you pick ahead of time with some energy fraction parameter, tells you how soft you want to go, as well as some angular weight parameter. It removes particles at the periphery of the jet and sort of keeps the hard core. That's what's called jet grooming, and you're looking inside the jet to do that, but there's phenomenological reason to want to do that. When you do that in the EFT, it introduces new scales in the problem, and it's kind of an interesting problem. So you groomed away these particles, kept the kind of central particles, and it ends up kind of in phase space. If you think about Z, which is a momentum fraction, and small z is higher in the picture, and theta, which is an angle, and over to the right is more collinear particles, you're removing some swath of soft particles. So it goes all the way to infinity here. And that kind of affects the modes in the EFT, and you get what are called collinear soft modes, which are a mix of collinear and soft. But you get, again, some kind of factorization theorems that can describe the problem, even in the presence of this jet grooming. So the jet grooming isn't making it harder to do it's making it in some sense easier to do the factorization because it's less dependent on the sensitivity to the things outside the event. And you can even use the EFT to talk about non-perturbative physics. So you could ask, here kind of was perturbative, everything was a perturbative description. How did non-perturbative patternization effects come in and affect the problem? And actually, that's not so hard. In an EFT context, you just write down some degrees of freedom for those non-perturbative particles. So that would be some modes that in phase space live at some point up here, where p squares of order lambda QCD. And then you think about those as just some fields that you have to treat non-perturbatively and figure out how they talk to other fields in the problem. And when you do that, you can actually derive factorization for non-perturbative corrections and figure out kind of counting of what the fundamental matrix elements are that are describing the hadronization. And this is something that we did for these soft drop groomed jets, and determined that there's actually 3 non-perturbative parameters and 2 perturbative Wilson coefficients that show up in the leading description of the hadronization. So even things like hadronization can be described in this EFT. But I'm out of time, so let me just come to my summary. So I only summarized here the applications. So there was applications to precision QCD, going to higher orders and logarithms and fixed order. But he skipped over the Regge. And then there was an application to power corrections for thinking about how to do power corrections in the EFT is pretty systematic. And then application to the grooming. So I'm happy to take questions about anything that I talked about.